Hi. In the previous segment, we reviewed some basic concepts involving sets. In this one, we shall look at how to define sets and some fundamental operations on them. The most straightforward way of specifying a set is by simply listing its elements between curly braces, like here. This can become tedious or impossible for sets containing many, even infinitely many elements. In this case, we use a syntax called set builder notation, or also set comprehension. It comes in two slightly different flavors. In the first form, there are two parts separated by a colon or sometimes a vertical bar. The first part introduces a variable, here the x, and the set its values are taken from, in that case the positive natural numbers, n+. The part after the colon lists conditions that have to be true for a given value of the variable to be an element of the set we are defining. So for example, if we pick the value 4 from the positive natural numbers and call it x, then it is only part of the resulting set if it satisfies the condition, which here is that x be prime. However, 4 isn't prime, so 4 isn't the value of x that ends up as a member of the set defined here. If instead we pick 17 for x, then the condition is satisfied since 17 is prime, and so 17 is a member of the set. Because these conditions can be thought of as filtering the values of the original set n+, they are sometimes also referred to as filters. The second flavor of set comprehensions also consists of two parts separated by a colon, but the first part does not really introduce a variable, but instead uses it. The part following the colon still contains conditions that must be true for any value bound to the variable, still x, to be used in building the elements of the set we are defining. For instance, the first example defines exactly the same set as the ones under flavor 1, but it does so slightly differently. The flavor 1 version said, this is a set of all values x from a set n+, the positive natural numbers, such that x is prime. The flavor 2 version says, this is a set of all values x, such that two conditions are satisfied. X is an element of n+, and x is prime. The resulting set is of course the same in this case. The second example illustrates a way of using this notation to make set definition a little more economical. It's the set of all 2x such that x is in n+, in the positive natural numbers. In other words, this defines the set of all positive even numbers. If you like, try to define that set using flavor 1 style of set builder notation, just to get an idea of the difference. The second flavor does give a bit more flexibility when writing sets, but it is not without its pitfalls. Here are two simple examples of flavor 2 set comprehensions that do not in fact yield well-defined sets. We will discuss this in a moment. Another way of defining sets is using what is called a recursive definition. This will become important later in the course, but for now we shall skip it and write large, even infinite sets by enumerating a few of the elements and then alluding to the principle used to construct it using ellipses. When using this kind of notation, it is crucial to be aware of its limitations. For example, is this a true statement? The answer is that the question cannot be answered because the set isn't really well defined, so we have no way of telling whether 12 is one of its elements. For example, the set could consist of all the numbers in a sequence that starts with 2 and then adds 1, then 2, then adds 3, and so forth, in which case the set would contain 12. Alternatively, it might be a set of all the numbers in a sequence that started with 2 and 3, and where the next number is the sum of the previous two, which means the next number after 8 would be 13, and 12 would not be an element. The bottom line here is this: we don't know because the notation we use does not really supply a full definition of the set in question. However, even though this isn't a full formal definition, this notation is sometimes useful when the rule for generating elements is obvious or understood from the context. Let us look at a few examples of set builder notation. Given the set A as defined, what are the extensions of B and C? B simply becomes A without the 2, and C can be computed by trying all the combinations of values for x from A and y from B that satisfy the chain inequality y less than x less than 11. Before leaving set builder notation and its use in defining sets, we should look at how not to use it. Consider this set R, consisting of everything that isn't an element of itself. At first blush, that might seem weird. Can sets even include themselves as elements? Well, if the answer to that question is no, that's fine. It just means that R is in the set, that R is the set of everything. If nothing can contain itself, it follows that everything does not contain itself. Either way, we should be able to ask, does R contain itself as an element? Remember that for any set, something either is or is not an element of it. So we should be able to answer that question by going to the definition of R. However, if we assume that the answer to that question is yes, that is, R is an element of R, it means it must have the property required by the filter in the set comprehension defining it, which was x does not contain x. In other words, if R is an element of R, it implies that R does not contain R as an element. That's not good. Since the assumption that R contains R leads to a contradiction, we conclude that R cannot contain itself. However, if it doesn't, it means that it suddenly satisfies the property defining it, which then means it is an element of itself after all. So if R is in R, it cannot be in R, and if it is not in R, it must be. This contradiction is known as Russell's paradox. It means that the above definition of R is not well defined and that really its definition is meaningless. But what makes it so? Why is it meaningless? What's the problem with that definition? When you use flavor 2 of the set comprehension, you're using variables without actually introducing them. In particular, you do not give a set of values that the values of the variable are taken from. In the definition of R, the variable x is two-free. It is not constrained to values from some known set, such as, for example, n plus in the previous examples. This is too much freedom. So when you use flavor 2 of the set builder notation, make sure that your filters constrain the variables that you're using so that they can only assume values from previously constructed sets, or sets that are generally known, such as the natural numbers or the real numbers, etc. Let us now look at a few simple operations on sets. The first one is union. denoted by that stylized U. Given two sets A and B, their union is the set of all their elements combined, or more formally, a thing is an element of the union if and only if it is an element of at least one of the sets A and B. By contrast, the intersection of two sets, denoted by the stylized inverted U, is just the set of all things that are in both A and B. Finally, the set difference between A and B, denoted by the backslash, is the set of all elements of A that are not also in B. With this, we can also define what it means for two sets to have no common elements. That is, what it means for them to be disjoint. Two sets are disjoint if and only if their intersection is the empty set. Note that every set is disjoint from the empty set, including the empty set itself. This idea also generalizes easily to more than two sets. We say that a bunch of sets A1 through AN are pairwise disjoint if no two of them contain any common elements. That is, if every pair of them is disjoint. Using these operations, it is possible to compute with sets in a way that is not too different from how one computes with numbers, including a variety of rules for transforming expressions involving sets and operations on sets. You're not expected to learn these rules of the set algebra, but you should be aware of their existence, and there's more material on that topic in the textbook. To summarize, we looked at different ways of building sets, as well as some of the issues that arise by discussing Russell's paradox, and how to avoid using set comprehensions incorrectly. And we also discussed a few basic operations on sets. In the next segment, we shall look at working with multiple sets and also the notion of a power set.